Hello, my name is Taewoo Kim. At ETRI's Social Robotics Research Lab, we have been conducting research on learning catching skills using bimanual robots. Today, I will present our study titled Learning Dexterous Bimanual Catching Skills through Adversarial-Cooperative Heterogeneous-Agent Reinforcement Learning. In daily life, humans often catch flying objects with their hands. This skill enables fast object transfer for efficient task execution and plays a critical role in sports performance. Depending on the object's characteristics, humans naturally use both hands to ensure a stable grip even for small objects. Bimanual catching skills can increase the success rate of catching and mitigate the difficulty of dynamic tasks. In this study, we propose a method to train bimanual robots to learn catching skills. Additionally, we introduce a throw agent to optimize catching skills using heterogeneous agent reinforcement learning framework. Previous research has explored object throwing and catching with robotic hands. However, most studies focused on short-range, single-handed interactions, often with simple object shapes. Some studies were conducted entirely in simulation using floating robotic hands, making them unrealistic for real-world deployment. These early-stage studies did not fully consider human-like dual-arm and dual-hand structures. Therefore, we argue that research on bimanual catching for humanoid and dual-arm robots is essential to further advance robotic dexterity. Our study offers three key contributions. First, unlike previous single-handed catching research, we focus on bimanual catching skill learning. Second, we introduce an adversarial cooperative framework with a dedicated throw agent, enabling an adaptive learning curriculum for optimal skill acquisition. And third, we validate our method with 15 diverse objects, demonstrating its effectiveness in generalization. We adopt a heterogeneous agent reinforcement learning framework utilizing the PPO algorithm to train two agents, thrower and catcher. Catcher learns to catch using reward signals based on object pose, proprioceptive data, and hand object distances. Thrower receives full environment state and episode terminal signals, controlling the initial velocity of thrown objects. The adversarial cooperative interaction works as follows. If the thrower increases the throwing velocity, it receives a higher reward, but the catcher's task becomes harder, leading to a lower reward. Conversely, if the thrower slows down, it gets a lower reward, but the catcher benefits, making it a cooperative behavior. This adversarial cooperative relationship enables the catcher to optimize its catching skills efficiently. Our training follows the centralized training with decentralized execution paradigm. Using HAPPO, we optimize the objective function with a compound policy ratio for both the thrower and catcher agents. For more details on the HAPPO formulation, please refer to the paper. The key aspect of adversarial cooperative learning is reward function design within the HAPPO framework. The balance between adversary and cooperation is controlled by alpha, a critical tuning parameter. The optimal alpha value is determined experimentally as explained in the experiment section. To evaluate the effectiveness of our method, we conducted experiments with 15 objects. These objects include 4 primitive objects: gym ball, bowling-sized ball, cube, and board, and 4 YCB objects: banana, meat can, mug, brick, and 7 Videx hands objects: kettle, bottle, cup, bucket, pan, pot, and scissors. Here are the training results. Successful catches, unstable cases, and failure cases are shown. We also include a comparison with single-agent training results. To evaluate the effectiveness of our heterogeneous agent approach, we compare it with single agent, a baseline with only the catcher, and SA with PBT, a population-based training variant. HA with alpha decay, a model where alpha decreases from 1 to 0.7 over training. For evaluation, we removed the thrower and used a uniform random throwing environment. Our proposed HA method achieved over 2 times higher rewards than SA models. Alpha decay led to unstable learning, and the optimal alpha value was found to be around 0.7. We further tested our method in out-of-distribution environments, increasing the noise scale to 1.2 and 1.5. Results show that the HA Alpha 0.7 model maintained the highest performance even under challenging conditions. Overall, the HA approach consistently outperformed SA methods. Additionally, we analyzed per object performance. Large objects like gimbal, board, and pod had low success rates. However, when trained exclusively on large objects, catching performance improved, indicating a dataset imbalance issue. In this study, we applied heterogeneous agent reinforcement learning to train bimanual catching skills. The adversarial-cooperative reward structure significantly improved dexterity and adaptability. The throw agent dynamically adjusted the difficulty, leading to optimized catching performance. However, there are limitations. Simulation-only training requires real-world adaptation. Limited object set needs further generalization studies, and stationary agent assumption. Future work should explore mobile manipulators and humanoids. Beyond catching, our adversarial cooperative learning framework could be extended to collaborative assembly, dexterous manipulation, and multi-agent coordination. Our future goal is to deploy this framework on real robots and expand its applicability to dynamic environments.